Hi, this is Kan-Lin speaking. I'm from the National United University Department of Energy Engineering. In this unit 06, we're talking about the potential control. That means the electric potential was in a certain type of control manner, and then we observe the current at a different electrochemical process and see what will happen. The first one is a potential step method. In this one, we try to control the potential at the mass transfer limited condition. That means electron so negative or so positive, so the active material as soon as they diffuse to the surface and will be consumed right away. And then this electrochemical reaction is irreversible, so we don't need to consider the reverse condition. Under this circumstance, if we apply a potential step, and what it will happen. Let's say over here, if we consider an oxide O and be reduced into the R reductant. And by doing this, is we set the potential, as you can see, from the E1 and then go to the E2 at a time equal to 0. So when the time equals 0, we suddenly change the electric potential from E1 to E2. And what will happen is over here we think is over here in this side is the electron, and then this one is a solution. So at the x equal to 0, that is at the interface, electron solution interface over here. So inside the solution, when the x greater than 0 is inside the solution, at the time less than 0, that means the potential at hold as E1. In this condition, there's no electrochemical reaction taking place, so the concentration of the O species is supposed to be uniform over the entire solution, and then the concentration we designed as designated as a C0 star. But as we started when the potential at a time greater than 0, this period, then the potential was changed suddenly from E1 to E2, and the solution concentration will be changed at the time 0, maybe something like that. Important thing is over here is at x equal to 0, the solution, the concentration at the interface, that means right at the electron surface, is equal to 0. The CO, we call the CO, is equal to 0 in this condition. And as we start to keep let the time go by, and at the T2, the solution concentration profile in a solution is making like orange, the line, the T2, because the solution, the concentration of all species was consumed at the electron surface, so it had to be diffused and then make any compensation, replenish the O species which consumed at the electron surface. But however, the potential is set at E2, so it doesn't matter, the surface concentration always keep at 0. That means the mass transfer control, because the reaction at the electron reaction is so fast, the concentration at the electron surface equal to 0. And then at the T3, the concentration profile will be something like that. We call the boundary layer, concentration boundary layer. It means whatever this is the boundary layer. So from here all the way to here, this the boundary layer thickness delta. It will be keep increase. The effect of the solution concentration will be penetrate into the solution as the time go by. So the current we detect at the electron surface is supposed to be equal to the diffusion. That means the current we generate at the electron supposed to equal to the diffusion, the species diffusion to the electron surface. So So the I, the current, is a proportion to the concentration gradient at the electrode surface. This means the concentration gradient at the surface. That means the slope, the concentration profile slope at the electrode surface, right at the interface. You can see as the time goes by, the slope is getting smaller and smaller. So if we plot the current, and it's given like the black line here, that's the concentration profile. If we plot the current at a different time, it will given like this. At the time 0, certainly we change the potential from 1 to E2, E1 to E2. Then the current almost go to infinity, very large. And then it drop quickly, and eventually getting slow decrease as the time go by. Eventually go to some kind of relative steady state, kind of steady state. This can be analytical solve this current as a function of time. Let's see. We try to obtain an analytical solution for the current as a function of time. And on the figure on the top, actually, we described in previous slide. And then the potential was changed from the E1 to E2 at a time equal to 0, suddenly. And then the corresponding concentration profile in a solution, and it will be changed gradually as the time T1, T2, T3 is a solution profile will keep changing. And on the electrode surface, the current detected in the electrode will be at the time 0 almost go to infinity, and will be decreased dramatically, and then gradually get slowly gradually go to 0 eventually, but it takes quite a while. Let's see if we make a material balance at a given location, for instance, at a given location. And then within this boundary inside, then there will be material will be flow from the old species will be flow from the outside, go through here, and then diffuse over to the left side. From the right side, go to the left side. And then the species may be accumulated inside or decrease over here. You can see that within this boundary, actually, the species at the beginning is almost at this location, and then at the T1 is still the same, and then T2 and then T3, the concentration inside this box is decreased. So it depends on how much the material diffusing in and diffused out inside the box. So we can make a material balance, so-called Governor equation. On the left side, tell me that for a given time, what the species O as a function of time will be decrease or increase. The reason for decrease or increase because of diffusion from the left side to the right side. If the left side is much slower than the right side diffuse out, then the concentration inside the box will decrease. If the left side, the diffusion rate going to the box is much faster than the right side, the diffusion rate going outside the box, then the concentration will be increased. But from here you can see the concentration diffused inside the box is much slower than the diffusion outside the box, so the concentration will be always decreased. And since this partial differential equation is a respect of the t, respect of t, and then the second order respect to x. So we need, in order to solve this equation, we need one boundary condition respect to time, and then two boundary condition respect to x. Usually for the time, is the initial condition. That means at the time equal to 0. So the boundary condition, actually this we may call the initial condition at the time equal to 0. That means at any place, all the concentration inside solution equal to CO star here. That's called the initial condition actually, or you may say the boundary condition as a respect to time. And then for the x, because there's a second order respect to x, so we need two boundary conditions at x. At the x equal to 0, the concentration always equal to 0 because we control at the mass transfer limiting condition. So the concentration at the x equal to 0 always equal to 0 here. That's the one boundary condition. And the second boundary condition is at x equal to infinity. This doesn't matter within our experiment. This is far, far away. The concentration always equal to CO0 here when the x go to infinity. So with this boundary condition, we are able to solve the concentration profile and the current, diffusion current as a function of time that we call the Controll equation over here. Over here, the ERF is an error function. If you're interested, you can check on Google. You can find out what does it mean error function. It can be solved in this find out. The important thing we'll see with this equation what we can come out. This one, if you're interested, actually you can see the Allen bars, the electrochemical method. They will describe the detail how the equation was derived. But over here, I just briefly describe how it's come out. With this government equation here, that goes through called the Laplace transfer, convert all the t domain into the s domain here, into the s domain. So in this case, we convert a partial differential equation become the ordinary differential equation because the time is go to the s domain, and then we solve this equation in the s domain, the concentration profile, and then inverse the Laplace transfer, transfer the s domain into the time domain. We got the concentration as a function of time like this. And since the concentration, the mass transfer diffusion equation, the current detect equal to the concentration gradient at the electrode surface at x0. So we can substitute the concentration into this equation, differential against the time. We end with this equation they call the Controll equation. Now, the detail, if you're interested, you can look at through the textbook or check the this slide. You can see how it's come out. The next slide, we can talk about how to apply what application for this equation. Can check anyway. Since this calculate the concentration profile at a different time as a function of a solution x at a different time period, and then this is the plot of the diffusion mass transfer rate controlled limiting current, mass transfer limiting current as a function of time over here. So from this equation, you can see the ID. If you plot against this term, then you end up with a slope. The intercept should both 0 and then slope equal to NFAD and the C star over here. The D is the diffusivity. So if you plot the current, just as I say over here, the current over here against the pi t, square root of pi t, and 1 over square root of pi t, then you end with the slope, something like over here. So with this equation, you can check there's different things you can look at. First, if you apply the potential and then you record the current as a function of time, if you plot the current against pi or the t square root of the t, then if you got the linear behavior and with the intercept almost close to 0, then you can say, well, you control the potential is at the mass transfer limiting current condition. This potential is so negative or so positive, so the material at the surface almost equal to 0. The current measurement actually equivalent to the mass transfer rate. And secondly, you can measure the diffusivity or the concentration by plot this solution. And if you given a solution, you already know the concentration. Then from the slope, you can calculate diffusivity. You can estimate a diffusivity. Or you already know the diffusivity. Then you plot it this way. Then from the slope, you can evaluate the concentration of the unknown species. So that's some application for this Fourier equation.